Hello, everyone. Thank you for having me here. My name is Seung-gi Min. I recently graduated from Columbia Business School, and I just joined KAIST in South Korea as an assistant professor. So today I'll be talking about how to improve Thompson sampling, which is a very famous Band-Aid algorithm, by the use of policy gradient method. So this is a joint work with Siamang Moalimi and Ben Russo, both are from Columbia Business School. So I believe many of you are already familiar with this multi-Band-Aid problem, but let me introduce the Bayesian notation. So we'll be given a set of actions that we can select at each time, and each action will yield a random reward drawn from some unknown reward distribution. And this unknown reward distribution will be parameterized by some unknown model parameters, theta. And our goal is to maximize the total reward, which is equivalent to minimizing the regret. And today we'll be focusing on the Bayesian setting where this unknown model parameters theta will be treated as a random variables. And we have some beliefs on the distribution of this model parameters theta. And as a performance measure, we're going to utilize the Bayesian regret, which is the expected value of the regret over the randomness of this unknown model parameters theta. Great. And as you may know, there are tons of variations like linear or contextual or non-station bandits. So the framework I'm gonna illustrate today will be can be also applied to all these settings, but I'm gonna describe the framework based on this simple setting. So let me illustrate the main idea of Thompson sampling. So it is a Bayesian algorithm built on the top of Bayesian inference logic. So at a particular moment, we're going to have some observations we have observed so far. And according to the base rule, we can compute the posterior distribution of this unknown model parameters, random variables, theta. And Thompson sampling implements a randomized arm selection rule on the top of this Bayesian inference logic. So it takes two steps. So in the first step, it samples the model parameters from this posterior distribution. So a random sample of the model parameters will be drawn from this current belief and will be denoted by tilde theta. And the second step, it will temporarily believe the model parameters are the ground truth and select the optimal action. So we'll select the one with the largest mean reward given the model parameters tilde theta. And after selecting an action, we're going to have one more observation. And according to the base rule, again, we can update our posterior distribution. And this procedure will be repeated to the end of the horizon. So this is the main idea of Thompson sampling. As you can see, it's very simple and straightforward. It is also very computationally efficient and is known to achieve asymptotic optimalities in many settings. However, it's not always perfect. It fails to achieve the optimal exploitation and exploration trade-off, particularly in the following settings. So for example, we may have too short time horizon or too many arms. So in this case, we don't have enough time to explore every single arm. So it's better to exploit rather than explore. But Thompson sampling does not incorporate this time horizon information in its arm selection rule. So we'll continue to explore to the end of the horizon. So as an extreme example, suppose we have an infinite number of arms, then Thompson sampling will keep selecting a new action every time from the beginning to the end, and which is very suboptimal behavior. As another example, the arms may have different noise variances. For example, this arm may be easier to learn, whereas this arm may be harder to learn. So in this case, we're better to try out this arm first because we can quickly learn about this arm and quickly decide whether to keep it or discard it from our consideration. But Thompson sampling does not incorporate this noise variance information into the algorithm, into its arm selection rule. So it will treat them all equally likely if all they have the same priors. And there can be some free exploration effect. So this arm in the middle may reveal some information about the other arms. And in this case, we're better to try out this arm first. But again, Thompson sampling will treat them all equally likely if all they have the same priors. So to summarize, we can say Thompson sampling tends to overexplore. It's somehow overly optimistic about how much we can learn in the future when selecting each of the actions. And there can be a simple heuristic modification of Thompson sampling to fix each of these issues. But we are more interested in developing some general framework that can improve the Thompson sampling in some principled ways. And the basic approach we are taking is to take the dynamic programming perspective. So in the Bayesian setting, this multi-embedding problem can be viewed as an MDP problem. And of course, the Bellman equation for this MDP problem cannot be solved explicitly, so we can implement the optimal policy, but we can still characterize Thompson sampling, understand Thompson sampling as a very effective heuristic policy that solves this MDP problem. And we can utilize the modern dynamic programming techniques to improve Thompson sampling by leveraging the computing power and also by exploiting the structure of the problem. So with the same goal, in the past, we have suggested two approaches with different modern dynamic programming techniques. And today we'll be focusing on the more recent one where we utilize the policy gradient method. So it was a long introduction. So let me illustrate the main motivation of this paper. So if we are simply trying to avoid the overexploration of Thompson sampling, we can just scale the posterior distribution that Thompson sampling will use. So for example, if the standard version of Thompson sampling is sampling the model parameters from this Gaussian distribution, normal distribution, we can simply add a tuning parameter or a meta parameter, lambda, in front of this variance term to scale the variance of this posterior distribution. This is to control the degree of random exploration the algorithm will conduct. So if this lambda is chosen to be 1, it will reduce us to the standard Thompson sampling. And if we take the lambda smaller than 1, the resulting algorithm will perform less exploration than standard Thompson sampling would do. So we don't need to stop here. The correct prior is not necessarily the one that maximizes the performance of the algorithm. So we can make the Thompson sampling to use its own prior, like different prior than the correct one, which is intentionally misspecified. So far, so good. But the thing is, it will be very challenging to find the right values of these tuning parameters or the meta parameters lambda. We don't know how to do it in an analytic way. So what we are suggesting is to use the policy gradient method to find the best performing meta parameters lambda in some data-driven way, possibly starting from the standard Thompson sampling. So far, so good. Let me skip this literature part because of time limit. So the policy gradient is nothing but just stochastic gradient ascent algorithm applied for these randomized policies. So at each iteration, at each policy gradient iteration, it is trying to update the values of this policy parameter lambda in a direction that can increase the performance of the algorithm. And this direction will be given from this gradient estimator. So after a single round of the pi, we can compute the gradient estimate of the gradient the estimated gradient of the performance of the policy. So in a nutshell, it is trying to increase the likelihood of the action that have yielded the high reward after that action. So this is a general framework of policy gradient, but unfortunately, it doesn't work for Thompson sampling as of now. The issue is, in order to compute this gradient estimate, we need to compute the gradient of the log likelihood of the action selected by the algorithm. But in case of Thompson sampling, the likelihood of the action is intractable most of the cases. If you remember, the Thompson sampling's action is the optimal solution to a random instance of some optimization problem. And most of the cases, we don't know how to write down the formula for this arm selection probability. So we cannot implement the policy gradient for Thompson sampling at this point. So before talking about how to fix this issue, let me illustrate how to parameterize Thompson sampling. So this is the workflow of standard Thompson sampling. And we introduce the meta parameters, the tuning parameters, or the policy parameters lambda to parameterize, to generalize the distribution, the sampling distribution that this Thompson sampling is sampling the model parameters from. So we are not restricting a particular form of parameterization. Of the following can be useful examples. So as we illustrated before, we can introduce a single parameter, a tuning parameter lambda, to scale the variance of the sampling distribution. Or more generally, we can, if the standard version of Thompson sampling is utilizing some exponential family distribution as a posterior distribution, we can introduce a mapping from one sufficient statistics to another sufficient statistics to reshape this posterior distribution. If this mapping is an identity mapping, then this is going to be reduced to standard Thompson sampling. If we can parameterize this mapping, we can consider an arbitrarily reshaped posterior. We can also completely replace our inference logic, the Bayesian inference logic, with our own inference logic that is implemented with some deep recurrent neural network. So these are the example of the possible parameterization scheme. But still, as we discussed before, we cannot implement the policy gradient because in order to compute the gradient estimate, we should be able to compute the likelihood of the action taken by the Thompson sampling, but it is intractable in most of the cases. So here comes our main idea. So we instead, we interpret the sample, the model parameters, tilde theta, as a pseudo action taken by the Thompson sampling. So this is the decision made by the Thompson sampling. And because we have parameterized, we know how to parameterize, how we parameterize this sampling distribution, we should be able to compute the log likelihood of sampled model parameters, as well as its gradient. So we can compute the gradient estimate, and so we can apply the pulse gradient. So this is a very simple tweak. It's seemingly very obvious, but it's obvious once we knew the answer. I'd like to say it is not so trivial as much as anyone can figure out easily. So anyway, with this pseudo action interpretation, we can compute the gradient estimate in a tractable way. And we have a couple of more suggestions to reduce the variance of this gradient estimate, gradient estimator using the notion of reward metric and baselines. But I'm not going to the details, but this is kind of realization of Rao and Blackwellization suitable for the Bayesian multi-amenity problems. And we have some theories basically suggesting some ordering among our suggestions. So sorry for skipping all the details, but let me dive into the numerical simulation part. So I'm showing it. So this is a very standard setting of a multi-ambiguity problem, and I'm showing you the regret of the algorithm over the course of the training. So starting from the Thompson sampling, at each policy gradient estimator, I'm computing the gradient estimate using the pseudo action interpretation and update the model parameters, update the meta parameters or policy parameters lambda according to the policy gradient step. And these are the curves with different choices of reward metric or baselines. And as you can see, after a couple of days of training, we can reduce the regret of Thompson sampling by 22%, which is very comparable to the other state-of-the-art algorithms. And we can basically apply the same idea to another setting where we have too many arms or too short time horizon. And you can see we are achieving like 30% reduction in terms of regret. One interesting fact here is that I'm running the exact same lines of code with the previous setting, but the algorithm somehow learned how to exploit this particular setting. And if we have a closer look at how it achieves, we can see the trained algorithm, trained Thompson sampling, is breaking the symmetry among the arms and somehow intentionally killing some of the arms, this group of the arms, as if it recognized it is a waste of time. So this algorithm learned how to exploit this particular setting, even though we didn't specify how to. Great, and we can apply the same idea to the non-stationary setting or to a more realistic situation, the news article recommendation example. So this is the example of contextual bandit problem, and we can see the Thompson sampling can be improved a lot after the training. So great, let me wrap up the talk. So we discussed how to improve the Thompson sampling using the policy gradient framework. So basically we are achieving the goal of meta learning. We are learning how to learn in a data-driven way. And by using the Thompson sampling as a starting point, the resulting policy, the trained algorithm, will be guaranteed to perform better than Thompson sampling, which is already good, while preserving all the nice properties that Thompson sampling has. So basically it can be implemented wherever Thompson sampling can be implemented. And we discussed the simple tweak that allow us to apply the policy gradient, which is seemingly not working for Thompson sampling at a first look. So with this framework, we believe you don't need to develop any application-specific analysis. We can just let the computers do the job, and the computers will learn how to achieve the state-of-the-art performance we're using the computing power. And as we skip, even though we skip this, but we are also suggesting the techniques to reduce the variance of the gradient estimator in the Bayesian multi-bandit problem. So thank you for attending this talk. The paper is available online. So if you're interested in, then you can look for the paper, and I'll be happy to answer any question. Thank you.